Okay, let me just check that we're recording. Okay, looking good. Okay, so off we go. Real quick reminder, don't forget about the attendance quiz. Code on the board there. Got a little less than 2 minutes left. Okay, moving along. So last time we were talking about how to do second derivatives with the multivariable chain rule. And so we've already kind of gotten started with the example. Well, this is a topic that I really do think is best covered just by example. You get the hang of it. So we've already talked about how to compute a first partial. That's really kind of old news. If you're interested in the partial of that with respect to that, we identify that there are two paths. We write down the corresponding terms to give us our effective multivariable chain rule, and then it's plug and chug. I mean, we know how polar coordinates works, and we can take those partials, and I think that's about where we left off. Okay. All right. So now, keeping in mind that our goal was to compute the R partial of the R partial, we're going to need to take an R partial of the R partial that we just computed, namely that. Okay, so plugging that in, we now see what we have. Okay, now let's be a little bit careful about this. Let's see here. We're taking a partial with respect to R. Okay, partial with respect to R means that's what we're taking the partial with respect to. That means the other variables in its world are to be understood to be constant. That means theta is going to be constant. And here's the thing, if theta is constant, then so is cosine theta, and again, so is sine theta. Constants, right? And because those are constants, we can not only separate the terms, we can also factor out those constants. Okay, so that's how that next step works. And that leaves us then with a little bit of a weird question. And let's see here, just for dramatic purposes, let me scratch this off for a moment. That's going to be the answer to the rhetorical question I'm about to pose. And that is, how do I make sense of the idea of the rate of change of a partial derivative with respect to a variable, right? We've talked about the rate of change of a variable with respect to a variable, but what's that? What are we how do you make sense out of that? Now, what you can't do, what's going to be very tempting, and I emphasize the following as usual because I see students step on this landmine a lot, and I want to minimize this, and I've noticed over the years, the more I dwell, the less I see this little catastrophe happen. But it's tempting, whoops, wrong color, tempting to call that ZXR. I claim that this is total nonsense, doesn't make any sense at all. I don't even know what you're talking about there. So let me try to explain what the problem is here. This suggests that we have a variable z that is a function. Let me get rid of all of that. That we have a variable z that is a function of a collection of variables in. Wrong color again. I'll use green. A collection of variables that includes both x and r. It's like we're viewing z as a function of all of those variables. And you can't do that. It doesn't make any sense. Those variables aren't independent. The x's and the y's depend on the r. Right? It just doesn't make any sense. So, you can't do that. Make a point, please, of not doing that. Very important that you not write down garbage in the part of your solution, right? Okay, so back to the same concern then, well, then how do I make sense out of this? Okay, and the answer is actually pretty satisfying. It's what I have written up here. If you have, let's say, z that's a function of x and y, so are its partials. Right? Easy example. You can look back at the very first few examples that we wrote down of how to take partial derivatives. You have some expression involving x's and y's. You take an x partial, you get another expression involving x's and y's, right? So along those lines, I'm explicitly going to note that on my diagram. And again, the diagram's your friend, you gotta love it. So, partial of zx, let's see, well, what is zx? Well, again, because z is a function of x and y, zx is a function of x and y, and I'm going to indicate appropriately on the diagram. Likewise for zy while we're here. Zy, also a function of x and y. Indicate so on your diagram. So now, the question of how to make sense out of this partial is not a problem at all. Zx, okay, that's there. And let's see here, taking a partial with respect to r. Okay, well, r is there. Cool, I have two paths, thus giving me two terms. Let's see here. Oh, color choices. Let's see. Here's the x term. Right? And then here's your y term corresponding to your two intermediate variables, x and y, which I have identified effortlessly from the diagram. Right? Keep track of your diagram. Keep your diagram fully up to date. Right? As you introduce new things, you need to take derivatives of. And, there you go, chain rule. Right? So this is, how you handle that kind of a situation. Just make sure to interpret the thing you're taking a partial of appropriately in terms of what is it a function of. Okay, now, proceeding along, let's see, so this is, that partial is that. Don't forget cosine theta. Constant, multiplicative constants, they just come along for the ride, right? So that continues there. Now, the next term we're going to handle very, very similarly. How am I going to understand the partial of zy with respect to r? Okay, well, zy, function of x and y, there it is. Partial with respect to r, there it is. And again, a path gives me a term. Other path gives me my other term. And, as before, multiplicative constants come along for the ride. Everybody on board? So really, the way you deal with second derivatives is just make sure to rely on your diagram. Go slowly and carefully. Don't write down a bunch of stuff because it seems symbolically that's, what the symbols ought to look like. Maintain your diagram. Rely on your diagram. Keep your diagram updated. Do exactly what the diagram tells you to do, right, along these lines. And then just, slowly and carefully. Right? Don't try to do too much all at once and, miss factors and, considerations and stuff. Okay, so it's all over but the shouting at this point. Y'all can read through the rest of this. Again, it's easy to take partials of polar coordinates. That's, chapter 1 stuff. And there are notational simplifications to be made. That's perfectly fine. Z is a function of x and y, so Zx is a function of x and y, and so we can directly talk about its partial with respect to, take your pick, either x or y. All of that, perfectly fine, no problem. Okay, and then the last step is just some simplification. Collecting terms, that kind of thing. Okay, so there you go. Now, not all of these look exactly the same. Sometimes it's a little different. There is a homework exercise where instead of taking the r second partial, as we did here, where you will instead take the theta second partial. And things go down very analogously with one significant difference, and that is, you'll notice what happened here. Our r partial of x didn't have any r's in it. And that's why we got to treat this as a constant, and we got a nice little simplification there. When you're doing the theta second partial, you'll be looking at the theta partial of x, which does have thetas in it. right? So you're not going to have a constant there to deal with. You're going to have to use a product rule, right? So things will change just a little bit. Heads up, again, rely on the diagram. Don't go too quickly, and always be thinking about what's a function of what and what's playing what role, what's a constant, what's a variable, etc. So other than the product rule that shows up, it's very, very similar. And I think that's a homework exercise, if I remember correctly. So y'all will get practice doing that. Okay, so I want to show you a neat application. This was the application that motivated me to put second derivatives in here in the first place. You may recall it's actually not in the book. The second derivative stuff with the chain rule is it's on the content syllabus in the included material column, right? I felt like this was an unfortunate oversight, gap in what's in the book. And this is what made me want to do it. So, in my past life as a second major in physics, I had to do a fair amount with this thing called the Laplacian operator. And this is extremely useful in physics, which means it's extremely useful in engineering, which is where y'all are probably going to see it. And this is how you keep track there's a lot of details that y'all will see in other classes, but if you want to describe waves, well, it involves heavy use of the Laplacian operator. And if you want to keep track of how heat moves, heavy use of the Laplacian operator. If you want to understand how electrons behave, these are big applications, right? Huge applications. And there's a lot to say about them, and again, topic for another course, but the Laplacian is critical to all of those. Okay, so it turns out this Laplacian operator, you can see I've got it written in rectangular coordinates. All those partials are with respect to rectangular variables. If you want to write it in spherical coordinates, you can do so like this. And you're probably thinking the same thing that I thought the very first time I saw this, which is, yeah, thanks but no thanks. What a monster. That looks terribly inconvenient. Why would anyone with the right to choose ever choose that? Right. Okay. All right. And by the way, also, where does that come from? How do we know that's true? And we're going to come back and talk about that in a minute. Before I show you where it comes from, I want to try to persuade you that this is actually a good thing, that this is your friend. In many important situations, this is so much easier to work with than that rectangular formula right there. Because the world is full of circles, the world is full of spheres, the world is full of balls. Roughly speaking, spherical coordinates are very, very natural for such things. So let me skip down to the example, and I'm going to show you what's called Laplace's equation right here. And this is good for all sorts of neat stuff, such as understanding gravitational field, gravitational potentials, to be more careful, and electric potentials. Again, kind of a big deal, right? Something that we certainly need to understand. Okay, well, it turns out that, as you can see here, the Laplacian, major player, right? And there are functions that actually solve this, that satisfy this equation. Turns out this is a very natural solution to this equation. Everywhere except the origin, of course. Okay, so let's just talk about how to confirm this, right? If I wanted to confirm that that function does satisfy that equation, let's think through our options. Well, one thing I can do is I can take the rectangular Laplacian of the rectangular formula for f, and I can compute and ask if do I not get 0, right? And the other thing I can do is I can compute the spherical Laplacian of the spherical formula, you'll note there, for this function. Same function. Honestly, same Laplacian of the same function. This is just doing the exact same calculation in spherical coordinates instead of rectangular coordinates. And so again, I would need to compute all of this and decide if that is or is not 0. So now again, we're looking at our choices here. Which one of these calculations would we rather do? A lot of people are going to lean naturally toward the rectangular calculation. And by the way, that rectangular calculation is a good computation. Everyone should do it once in their lives. I'm pretty sure we have one such opportunity as a homework assignment for y'all somewhere in this course. I don't remember exactly where it is. I want to say it might be in 3.1. I'm not sure, but y'all will do this calculation at some point. It's not particularly easy in rectangular. It works out fairly inconveniently. All right, so I'm not going to go through that here. What I'm going to do is just put a kind of a frowny face on that, because that's no fun. But let's think about this computation down here. Turns out this computation is easy. So easy, we're going to do it right now. And I'm not even really going to have to write down any algebra to speak of. It's borderline a gimme that this is 0. So let me try to persuade you that that's the case. We've got 3 terms you see here, right? And all 3 of those terms are applying to this same function. So let's take these one at a time. Let's start by applying this operator to that function. And let's see here, the very first step in that process, you can see is I'm going to have to take a theta partial of something that doesn't have any thetas in it. 0. Gone. The whole term, poof, disappears in a puff of smoke. Because the very first computation I get is a 0. The theta partial of that 0 is still 0. When I multiply that next factor by 0, I get 0. We got 0. Right? So this first term, obviously, 0. Second term, very, very similar. You'll notice that when you apply that to that, the very first thing that happens is I'm going to take a phi partial of an expression that has no phis in it. Boom, 0, gone. We're done with that term as well. All of that goes to 0. Yeah? Everybody seeing why this is nice? This is really, really nice. Basically effortless. The last one, we have to do a slight little bit of work. It's not so bad. I do have to take a row partial. This does have a row in it, but that's an easy derivative to compute, right? What do you get when you take the row partial of constant over row? Well, you're going to think about the power rule, and it's going to have a row squared in the denominator. And with rho squared in the denominator, rho squared times that is a constant, and color choices, any sort of a derivative, doesn't even matter, any sort of a derivative of what is clearly a constant is 0. And we're done. We've computed that whole... It looked nasty. It looked like a terribly unfriendly expression that was going to take us... Oh my gosh, it looks like it was going to take us at least twice as much computation. But it's a snap. Everybody sold? Right? So I want to strongly encourage you. Now, times will come up in your engineering future when you get to decide what coordinate system you want to use. And don't get me wrong, rectangular coordinates is great in a lot of circumstances, but if you're talking about a situation like this, where we're talking about either the electric potential from a point charge, that's naturally radial, right? The spherical kind of aspect of that is intrinsic in the physical setup, right? Likewise, gravity from a point source, right? Naturally radial. There's naturally going to be a sort of a spherical simplicity to that. Don't cling to the rectangular coordinate system. Use spherical, for God's sakes. Right? Way easier to work with. And this is not the only example, not even close. Okay. Yeah, question?
If this is always equal to 0, how do we even use it?
Oh, well, it's equal to 0 for specifically this function. Right? So that function is the solution to this equation, which just what that means is that when you're looking at either a point mass or a point charge, then what I have circled in green there is a formula for the potential energy function for that scenario.
You always multiply that with your function.
Do what now?
You always multiply that with a function that you fix at the end, or
You talking about the F? Yeah. So F is the solution. It's that is what the gravitational potential looks like, or the electric potential. Yeah, and we know it works because we plug it into Laplace's equation and we get what we're supposed to get. Does that make sense? Okay. All right. I think it's a neato example. Okay, so back to where this formula comes from. So I hope I've persuaded you that this is a useful formula. Now let's try to figure out where it comes from, and I claim it just comes from applying the chain rule to this diagram. Now, there's a lot of details here. Like, really a lot. Like, I don't even think I'm going to encourage y'all to do this, right? There's a lot. But I do want you to understand how the calculation goes down, right? So that, God forbid, if you have to at some point in the future actually do this, I'd like you to know sort of, how that, what the strategy is. And frankly, it's a lot like what we've already done here, right? Looking back at what we've already done, we had a rectangular function interpreted in polar coordinates. Now, we're looking at a rectangular function reinterpreted in spherical coordinates. Pretty similar setup. And looking at what we did over here already, we've already talked about how to rewrite polar partials in terms of rectangular partials. Right? That's what the chain rule did for us, among other things, is it allows us to interpret the composed, namely the polar, namely the new coordinate system partials, in terms of the naturally stated rectangular coordinates partials that we presumably, at least in some contexts, might have an easier time with. So notice in that rectangular example, here's the formula from the previous page that we were just looking at. Now, I did write it a little bit differently. You're going to notice that there's no function. These operators are not being applied to any function, right? Where's the z? Okay, fine. All I'm saying explicitly is that these are the same as operators, and so namely, if you apply them to some function z, you'll get the same thing. In other words, effectively, just put a z there, and a z there, and a z there, and so now you get an equation that's literally exactly what's on the previous page, right? It's straight up application of the chain rule, nothing creepy. For your consideration, this kind of notation is fairly common. And you are going to see that kind of thing. When, in particular, what you're interested in is the operator. If the z is not what you're actually caring about, and if there's no confusion, if it's all the same, all of these apply to the same output function, then it's okay to just write this as a statement about operators. So heads up for that. Just be on the lookout. Don't get creeped out by it. That's all it means. Okay. So you can do that same thing for the theta partial. And again, you will, as part of a homework exercise. And having done that, notice you have a system of equations for x partial and y partial, which you can then just solve for using Math219, linear algebra methods from whichever linear algebra course you took. You can just solve for them, no big deal, and these are your results. And notice what I have then is I've taken, in effect, rectangular operators, and now I've got them written in polar coordinates. Right? So, what happens here is very, very similar, just lots uglier. And but that's strategically that's how the calculation goes. Okay. All right. Oh yeah. So last comment. These formulas here, very handy. Good things to know. At least good things to know where to find when you need them. Right? There will be situations where you have a function that's very naturally expressed. Oh, let's see. Let's look at this example. A function that's very naturally expressed in a non-rectangular coordinate system. And if your formula is written like so, very conveniently in a non-rectangular coordinate system, knowing how to compute the x and y partials, I mean, how would I even, oh my gosh, that'd be super inconvenient because, it's not written in rectangular coordinates. But knowing how to compute those in terms of, in this case, polar operators that apply very naturally to something that's written in polar coordinates. Right? Knowing how to take those easy partials on the right and assemble them to produce the rectangular partials you might need, pretty cool. Pretty handy. So, again, good to know where to find those when you need them. All right. Okay, moving along. So that finishes 2.5. Off to 2.6. 2.6, directional derivatives is a really neat idea, really important idea. Gradients, we've already seen a little bit, but we're going to do a lot more interpreting. We're going to make a lot more sense geometrically about gradients. In this section. So I'm going to start with directional derivatives, and to that end, I'm going to start with a quick summary of what we know about partial derivatives. Let's see, I can do it there we go. Okay, partial derivatives. Well, we know partials are the slope of the graph. We know partials are a multiplicative factor, interpreted blah, blah, blah. I haven't written the following down yet, but partial derivatives can be thought of by way of this expression, and it seems like a weird thing to write down, but this is a pretty natural expression. What this says is, look, if I'm at a point A, and if I am moving with that as my velocity, and therefore, this describes my motion in the domain. That's a pretty natural scenario that I'm at a certain point and moving with a certain velocity. Right? And keeping in mind, I am at that point because I plug in t equals 0, which makes this expression A. Right? So we're at the point A, literally. And in that scenario, where I'm at a certain point and moving with a certain velocity, you might want to know what's the rate of change of the function with respect to time. Right? This is a very natural little expression, and in this case, as I have it written here, this is the partial derivative. And this is a nice exercise, nice little chain rule problem. And I encourage you to do this. It's not that big of a deal. Notice that f is a function of position. Position is a function of time. Right? And we're taking the partial derivative of that f with respect to, wrong color, with respect to time. That's straight up, literally, a chain rule problem, right? So if you just apply the chain rule, interpreting this as a composition as we just described, write down the chain rule, you will get the partial of f with respect to xi. So again, nice exercise. I encourage you to take a whack at that. All right. Okay, so again, summarizing. Things we know about the partial derivative. Slope of the graph. Multiplicative factor. This new weird expression that we're kind of seeing for the first time. And then here's another odd thing to want to write down, but easy to verify. I mean, it seems a little silly, but the gradient being a vector of partials, when you dot it with a vector of mostly zeros, wherever that 1 is in the vector on the right, that's the coordinate of the vector on the left that is going to be the answer. Right? That's just an easy dot product. You just write it down, dot it out. There's only one term. And again, it is that partial. So again, make sure you can do that as well. Okay. 4 features of the partial derivative. Now let me rephrase this whole thing. These 4 things are equal. Right? These 4 things, now again, this applies only when you're talking about one of the standard basis vectors, right? You got to be moving in the standard basis direction there, a standard basis direction there. This E has to be a standard basis vector there. Likewise here, right? So these 4 green expressions are equal right now, all we know for any standard basis vector. And I don't want to say the word partial derivative anymore temporarily because I want to focus on these 4 things all equaling each other. All right. So here's the deep point. And this is I don't know, this is a little bit of a weird point. But what is a standard basis vector anyway? I claim there's something kind of arbitrary about it. And the big point here is this. Standard basis vectors are the result of making a choice about which direction your axes point, and that is an arbitrary choice. Completely arbitrary. It's something that you make up for your convenience in certain settings. But it is arbitrary. So just as an example, when I say it's arbitrary, let's look at this real world scenario. Maybe these are contour lines and I'm out for a hike, right? And these are level sets of the altitude function and, like so. And I'm interested in a scenario where I am at this point and I want to consider, maybe I go that way or maybe I go this way. Right? Okay, fine. But I'm out on the mountain. I'm not on a piece of paper. Right? I don't see any axis system. I'm a real person at a real place on a real mountain experience. I'm tired, right? It's real stuff. Right? And numbers you write down on a piece of paper are arbitrary nonsense. You make that, maybe try to help yourself represent that. So it's tempting to say, looking at those 2 vectors, that V is pointing in the direction of the y-axis, right? And W is not pointing in the direction of any axis. But that's only because you're making stuff up. If you just decide, I'm going to set the y-axis to be, a lot of people will pick north, I guess, right? Why? There's no reason. It's completely arbitrary. You can set your axes however you want. So yes, you could set your axes like this, and that's fine. But same scenario. Me at the same point. Me still contemplating these same 2 directions. I am completely free to set my axes like this. Right? Just make it up. So do whatever you want. So in the left choice, V is a standard basis vector. So let's assume they're unit vectors. V is a standard basis vector. But if I just set my axes up differently, like on the right, now it's not a standard basis vector. And likewise, W on the left, it's not a standard basis vector. Okay, but what are those arbitrary axes? If I set up my axes different, now on the right, W is a standard basis vector. Right? So really the point here is that anything that you do with axes, such as defining coordinates, is all made up and arbitrary. There's nothing intrinsic to the situation. Right? When you're out on a hike, you will not notice something magically happen when you're not walking exactly north anymore. No, not at all. Right? And so just depending on how you set up your axes, every unit vector could be a standard basis vector. Just set up your axes correspondingly. Let's take a pause on this real quick. You're all willing to buy this? Axes are arbitrary, right? Again, common choice to have your axes be east and north. It is arbitrary. Okay, so with that in mind, And going back up to here to what we concluded about partial derivatives. So, okay, partial derivatives. Well, these four properties that I have written in green. Well, now they only apply to standard basis vectors, right? Those what I have in purple. That's going to be a standard basis vector. Well, yeah, but any vector, any unit vector, could be a standard basis vector. So, here's the big conclusion, not only are these four expressions in green, not only are they all equal for standard basis vectors, they're equal for all unit vectors. And this is a really nice feature. Any unit vector, those four things are all equal. And so now, what are we going to call this? Well, the term partial derivative, tragically, we've already settled on that term, partial derivative, being something that comes out of coordinates. Right? We talk about partial derivatives with respect to specific coordinates. So we're stuck with that. And if I want to talk about a more general concept, I can't use something that is specific to coordinates. So we just have a new word. It's called directional derivative. This just means same thing, morally equivalent to partial derivatives, just with respect to a different coordinate system, you might say. But we get the same result, that these four things. Whoops, let me do it like this. These four things are always the same. So the name, again, we give is directional derivative. The notation we give is that right there. Right? Yes, to be fair, got to be clear about this. We are restricting our attention here to this V does have to be a unit vector, so that's still got to be a unit vector. That's still got to be a unit vector. Otherwise, you get into unit conversion problems, and that's not helpful. So we want to keep this to unit vectors for the moment. But all these things in blue, all equal. Very handy that they're equal. This deserves a name and a notation as we've just given them. Okay, pausing. What do you think? Everybody buying it? Okay. All right. Now I am going to point out a pretty cool notation. I think the slope of the graph thing, by the way, I think this is a pretty easy interpretation. Again, so we're moving in the direction of some vector, not in the direction of the x-axis, not in the direction of the y-axis, just some other unit vector. And well, that defines a direction, and that defines a tangent plane, a vertical cross-section plane, where I can look at that cross-section curve, and slope of the graph means, slope of the tangent line to that cross-section of the graph. It's just like with partial derivatives. But let's talk about this multiplicative factor thing. What do you think we ought to call the thing that we multiply by ds? Well, let me circle this better. The thing that I multiply by ds or ds dt to get df or df dt, right? I mean, what's the name? What would be a handy notation for that? And I think you're going to notice, if you think about single variable chain rule, right? And morally, this kind of is a single variable chain rule because f is entirely determinable based on s, based on how far you've moved away from that point A. And s is literally a function of t. So this is a single variable, a couple of single variable formulas here. You get this sort of apparent, faux cancellation that's actually not really that much of a problem in single variable. It's actually kind of okay. But df ds is a pretty natural thing to want to call it. So this is what I'm gonna call this the fifth equivalent thing, and And let's see here. So back to the colors. So yeah, the slope of the graph, the multiplicative factor, and because of this argument, that multiplicative factor is DFDS. So very handy. Definitely going to see that. Good thing to be aware of. Okay, let's do a couple of examples. Right, so here we go. Got some function here, and the question asks us explicitly what is the slope of the graph. And what makes this seem to be a hard problem is that it's a slope of the graph, but not in the direction of either standard basis vector. So not in the x direction, not in the y direction, but in the direction that this vector is pointing. Right, 3, 4 is pointing, kind of that way. It's not straight up. It's not straight to the side. It's at some angle. Right? So how am I going to find the slope of the graph in that direction? And hey, no problem. Slope of the graph, let's go back to here. Slope of the graph is directional derivative, which is computed by this handy dandy little formula right there. So if you want to compute a slope of the graph, boom, just do that. And you'll notice that's our first step, is to say slope is the directional derivative. Directional derivative is computed by that formula, and it's basically plug and chug on down with one little asterisk. I do want to point out the little asterisk. Remember, very important, the vector indicating your direction, the vector, in other words, that you are eventually going to be dotting with to get your answer, does have to be a unit vector in order to be able to have all the properties that we've got written down here. That's an important little asterisk. So we've got to look here and ask, is the vector that we were given describing our direction, is this a unit vector? And no, it is not. Right? So I need to find the unit vector that points in that same direction, and I think it's a pretty easy pitch. If I've got a vector whose magnitude is obviously 5, divide that by 5, and now you've got the unit vector pointing in that direction. So heads up, don't use the v that you're given. You do have to translate that into a unit vector like so. And then again, compute the gradient, do the dot, multiply it out, plug in the point A, bam. Everybody okay? Okay, another landmine. Another thing to be on the lookout for. Another easy mistake to make. It is easy to misinterpret the terminology here. Notice, let's just document on a picture. We've got this point 3, 1. That's our point A. And it says here that we're supposed to move in the direction of 3, 4. Well, as we just agreed, the direction of 3, 4 is that unit vector that points in the direction of 3, 4, and that is about like that. The misinterpretation that a lot of students make is to misinterpret in the direction of as toward the point. And that's a complete misinterpretation of what the question says. The question says we're talking about the direction of a vector. Vectors have direction and magnitude. This is saying, take this direction and magnitude called v, look at the direction, forget about the magnitude, but look at that direction indicated by that vector v. Vector has a direction and a magnitude. If you try to reinterpret that expression as toward a point doesn't have direction and magnitude. A point has a location. Now you're changing the statement. Right? So you really, really, really can't do that. If you interpret Again, 3, 4 now as a point, and I cannot emphasize enough, this is wrong. If you were to say, I'm going to interpret this as being the point 3, 4, again, big X next to it, that's wrong, right? But that's where the point 3, 4 is, and toward that point would be that direction. And you see, if you misinterpret this expression, then you would be literally going the wrong direction. All from a misinterpretation. Does everybody see the problem there? Okay, heads up, right? Be on the lookout for that. Don't misinterpret the language. I guess I'll leave that there. Okay, next example. Oh, yes, we have until 11. I don't know why I keep thinking I'm done at 11:05. Okay, we'll get this next example done, no problem. Okay, so we have here some temperature function. So temperature is a function of position, which, by the way, of course it is. Right? You think about in this room, for example, there's an X, Y, and Z coordinates we could describe for this room, and the temperature up there next to the light bulb, probably warmer, heat rises and all of that, probably warmer up there next to the light bulb than down here in the shade in a corner at a low altitude, right? So temperature varies with location, probably warmer by the windows. Okay, so if this were that function, and if I say, look, I'm going to be going in the direction that this vector points, that's the direction I'm going to be moving, right? So I'm going to be going kind of that way. As I go in that direction, maybe I don't know how fast I'm going to be moving in that direction. And I just want to know, look, per foot that I go in that direction, how fast is the temperature changing? Right? Does it rise by, 1/10 of a degree per foot? Or what? Temperature per unit distance. So that's our question. And again, reminder, DFDS is directional derivative, which again is computed by dot product with the gradient. So just another immediate application of directional derivative. Let me get my colors straight here. DTDS is directional derivative, which is computed with the dot product with the gradient. And now again, you do have to compute that gradient, and it's a little tedium to do. So you're going to have to take the appropriate partials to get that gradient. You're going to have to plug in the point where that's evaluated. All right, compute. And then, as before, just a dot product with the unit vector. So again, I just have to identify the direction. What direction? Let me get rid of the mess. What direction does that vector 2, 4, 3 point? What is the unit vector for that direction? Well, you divide by its own magnitude. Again, a little bit of arithmetic there. And then again, dot away. Right? And out comes your answer. Okay. Everybody happy? Okay. All right. Oh, let's see here. You know what? We don't have time to go through this next discussion, so I'm sure I owe you the, let's see here, the minute and a half. I'm going to let y'all out a little early here. Again, I'm sure I owe it to you. So we'll pick up here next time. See y'all later. Have a good one. Have a good day.